Hi everybody, and welcome back. Now in this video we're going to start the last section of the course, which will deal with optics and light. In this particular video we're going to look at the transmission of light through polarizing sheets. Keeping that in mind, take a look at the problem statement. As the problem states, we have light traveling in a particular direction and it's going to travel through three different polarizers. The initial light is unpolarized, but as it goes through these polarizers, it's going to line up direction with whatever direction the polarizer is. And what we're asked to find is the fraction of the original intensity that remains when the middle polarizer is at an angle of 90 degrees. Just to note, the angle is measured with respect to the y-axis, so I've drawn here a cross-section of one of these polarizers looking at it head-on. So imagine the light is coming out of the screen towards you. Then the polarizer angle is measured with respect to the vertical direction. So a polarizer direction of 0 degrees would be polarized in this direction, and a polarizer direction of 90 degrees would be polarized like this. Now, the problem also states that polarizers 1 and 3 are fixed. Their angles are set. We don't know what they are, but they're fixed. And we can change polarizer 2, and what we can do is measure the intensity that comes at the very end as we change the angle theta 2. For example, when theta 2 is chosen at about 10 degrees, so a little bit off the vertical, then we have a maximum of the intensity going through. Whereas when the angle is chosen at about 60 degrees, so about this much, then there's no light going through at all. So what we're going to do is use this information from this graph to find out what happens when the middle polarizer is at 90 degrees. Now, what we're going to have to do to find that is actually determine what the angles theta 1 and theta 3 are. In these types of problems, you're always going to generally be using the formula for the fraction of transmitted intensity between two polarizers. And that formula is the following. So I'll write it as transmitted intensity between two polarizing sheets. All it depends on is the relative angle of the polarization directions between those two sheets. And in particular, it's the squared cosine of that angle difference. So for example, if the polarizers are lined up, then delta theta is 0 because their difference is 0. The cosine of 0 is 1. That means that all the initial intensity will be transmitted through. On the other hand, when delta theta is 90 degrees, so they're at right angles to one another, in that case, you're going to have cosine of 90, which is 0. So none of the light will go through in that case. That's the information we're going to use. What happens when the angles are right angles to one another? And we see that we're going to have dips at 60 degrees when theta 2 is 60 degrees and when theta 2 is 140 degrees. What that means is that when theta 2 is at 60 degrees, either theta 1 or theta 3 has got to be at a right angle to it. Likewise, when theta 2 is at 140, so 140 is maybe like this, either theta 1 or theta 3 has got to be at a right angle to that. So what I want you guys to do is figure out what angles theta 1 and theta 3 have to be to produce these dips at 60 and 140, given the fact that they have to be at right angles to theta 2 in those cases. So figure out those angles real quick and we'll come back and finish up the problem. Let's first use the information from the first dip. We know that the first dip occurs when theta 2 is at 60 degrees. So theta 1 or theta 3, one of them has to be at a right angle compared to that. So for 60 degrees, we can add 90 to get 150. Or we can subtract 90 to get negative 30. Whichever one of those we choose, it'll be the same thing because a polarizer, if it's like this, minus 30 is equivalent to 150. It just depends on the direction, the parallel direction. So I'll just choose 150, and I'll write that as theta 1 must be 150 degrees. And let me go ahead and just draw a picture of what that looks like as the light is coming head-on towards you guys. So 150 degrees will be 150 degrees from the vertical direction, about that much. So the polarizer looks a little like that. And let's go ahead and just label the direction. For the second dip, it's at 140 degrees. So the other polarizer has to have an angle of 90 degrees with respect to 140. So I can subtract 90 from 140. To get 50 degrees. You could also add it, but that'll be the same thing. And that'll look like 50 degrees is about that much, so a little more than 45 from the vertical. Not that much. Now that we've determined theta 1 and theta 2, we can easily determine the transmitted intensity fraction when theta 2 is 90 degrees. So what we can do is just find out how much is remaining after each polarizer. So we have a light that's unpolarized first coming through the first polarizer. Some of it's going to be cut out. Then that light is going to be polarized with respect to the 150 degree direction. As it hits the second polarizer, it's now going to be polarized in the 90 degree direction, and some of it's going to get cut out. And then finally, as it hits the last polarizer, it's now going to be polarized in the 50 degree direction, and a little bit more of it's going to get cut out. To find out how much is remaining after each step, well, whenever you have unpolarized light coming through any polarizer, unpolarized means that it's going to have polarization in all directions. If it comes through any polarizer, always 50% will be remaining. And whatever light goes through will be polarized in the direction of that polarizer. So as we go to the first polarizer, half of it is cut away, and it's all going to be polarized in the 150 degree direction. So it's all going to look like that. So we're going to have 50% remaining after the first polarizer. Now that all the light is polarized in this direction, we have to use this formula. Okay? So between theta 1 and theta 2, how much is remaining is going to depend on the angle difference between these guys, which is 150 and 90. So the remaining light is going to be cosine squared of the difference theta 2 minus theta 1 is 90 minus 150. And then finally, now that all the light is polarized in the 90 degree direction, what's remaining as it hits the last polarizer is the angle difference between 90 and 50. Okay, and some more of it's going to get cut out. And how much is remaining is going to be the difference between theta 3 and theta 2. So 50 minus 90. You see that it doesn't matter which ones we chose for theta 1 and theta 3 because they're going to multiply them anyway to get the total intensity. If you multiply all this out, you're going to get a total of 7.3, sorry, this is squared, 7.3%. Okay. So that's the answer to the question. The remaining intensity fraction of the original intensity when theta 2 is 90 degrees is only 7.3%. So a lot of it does get cut out at each polarizer. And the final intensity, the final light coming through, not only is it only a fraction of what was originally transmitted through the first polarizer, but it's all going to be polarized in a particular direction. It's all going to be polarized in the 50 degree direction. So you're going to get polarized light that's only in a single direction after that last polarizer. Now, let me take this one step further. Even though this is the answer to the question we were seeking, let's take this one step further and just make sure our answer is consistent with other parts of this graph. What we can use is the fact that we also have not only minima at 60 and 140, which if we use to get this, we have maxima at 10 degrees and 100 degrees. So what we can do is make sure our formula makes sense with those maxima. How do we do that? Well, we have a formula in terms of, well, theta 1 is fixed and theta 3 is fixed, but theta 2 we can actually vary. So let me go ahead and write down a general formula for the transmitted intensity fraction, or just say the transmitted intensity, put this over here. So it's going to be theta naught, I naught times 1/2, general function of theta 2. Theta 1 and theta 3 are fixed. I'm just going to keep them where they are. So we have theta 2, which I can vary, minus theta 1, which is fixed. And then the last one is theta 3 minus theta 2. So theta 3 is fixed at 50 minus theta 2. What we can do, now that we have a general formula for the transmitted intensity as a function of theta 2, we can take its derivative with respect to theta 2 and make sure that it equals 0 when you plug in theta 2 as 100 or theta 2 equals 10. That'll tell us that it is either a maximum or a minimum, and that'll be consistent with our formula. So that'll give us another check on the answer we got earlier. So what I want you guys to do is take this guy's derivative, set it equal to 0, and then find out what that formula is. And at the very end, we'll use that formula to plug in those values and make sure it solves that formula. So take dID theta 2 equal to 0, get a formula, and we'll proceed from there. The equation you should get once you solve this equation is tan of theta 2 minus 150 equals the tangent of 50 minus theta 2. Let's make sure that these guys make sense with that. That should solve it for theta 2 equals 10 because the derivative should be 0 there. So if I plug in 10 degrees, I get tan of minus 140. Does that equal the tangent of 40? Plug it in your calculator, you'll see that it does. It's correct. Now for the other one we have at 100 degrees, Does it also solve it? Let's see. Theta 2 minus 150 is minus 50. Is that the case that tan of minus 50 is tan of minus 50? Of course. So both of those points are indeed maxima or minima. And so looks like our formula so far seems to be consistent with the other information from that graph. You could always go a little further and make sure that they're maxima, not minima, by not only taking its first derivative, but by also taking its second derivative and ensuring that the second derivative at those points is negative, as it should be for a maxima versus a minima. So you could do that to make sure 100% that those are indeed maxima. And you'll see that if you do that, you will get the correct answer. So this formula seems to make sense. So we've solved what we're looking for, but we are also able to check it with a little more information. Let me stop there and go ahead and take a look at the summary. If you have any further questions, take a look at the write-up, and we'll see you next time.